Hey class, Adam Ward here. During our lecture we started working on an adaptation of problem 5.10 from our textbook, and I want to go ahead here and work through the example problems that I had posed at the end of class. So our starting point is everything that we already knew from our previous example. Just to give you a reminder, we had a waste lagoon with 100 cubic meters per day flowing through it. We knew its volume and its depth, 1,500 cubic meters and 3 meters respectively, and an inflowing concentration of 20 milligrams per liter. And so the first thing we're going to do is stop from a conservative tracer or conservative pollutant that we were working with and ask, what happens if this thing's got a reactivity to it, or a first order rate coefficient of 0.01 per hour. So first task, steady state effluent concentration from the lagoon. In other words, what's the outflowing concentration? So we can write our normal mass balance equation for a CSTR. Accumulation on the left is equal to loads minus outflows minus reactions minus settling. And just to remind you, that concentration C, everywhere I've pointed at it with a pink arrow, that's the concentration in the lagoon. Now this is a steady state problem, so the accumulation will go to 0. And we weren't given anything about settling, so we'll take that term to 0 as well. And we find ourselves left with something like this. 0 on the left-hand side is equal to the inflow, 100 cubic meters per day, multiplied by its concentration, 20 grams per cubic meter. And in order to do that, we had to remember that load could be expressed as the inflowing Q, so Q in, C in, multiplied by its concentration. You also had to remember there that milligrams per liter could be converted into grams per cubic meter. In this case, it's 1 to 1. All right, reactive term, outflowing term first, 100 cubic meters per day times whatever that concentration is in the lagoon, and then our reactive term, where I've got our reaction rate, and I'm converting it from per hour into per day to make sure that all of my terms are dimensionally consistent, multiplied by the volume, multiplied by the concentration. And if we go ahead and solve this problem, we find an effluent concentration of 4.3 grams per cubic meter. Just as a reminder, that's in comparison to a 20 milligrams per liter if there was no reaction present. So that first order rate coefficient is having a substantial impact on what leaves our lagoon. Part B is more of a design application. So the owners of this lagoon are considering that we might want to change its volume to increase removal. And so maybe regulations have tightened, maybe they are feeling more environmentally conscious, maybe they want to lower that concentration leaving from 4.3 to perhaps 1. How could they predict the volume that they would need? So what we're asked to do here is derive a relationship that relates removal of a pollutant to the volume of a lagoon. And for this problem, I'm going to think about removal in terms of the outflow as a fraction of the inflow, or C out divided by C in. So we want that as a function of volume. Well, from our previous slide, our mass balance could be simplified to the terms I've written here. And if we divide through by the inflowing concentration and work a little algebraic magic, we can derive this equation at the bottom of the screen. So the outflow as a fraction of the inflow is equal to Q divided by Q plus K times volume. And I've gone ahead and graphed that up in Excel for you, so you can get a sense of what this might be useful for. So the case that we used for our calculation was a volume of 1,500 cubic meters, and what we found is that the effluent is just over 20% of the inflowing concentration. Now, if you wanted to use this in a design context, maybe your goal is actually not to remove as much, right? Maybe you only need that effluent to be 60% removed. So the C over C in would be 40%. You'll have knocked it down to 40% of its inflowing concentration. You could start there, bounce over to this design equation, and find that you need a volume of about 600 cubic meters. And of course, you could use the equation that underlies this to calculate the exact number. So this is the sort of exercise you might go through as a designer, where you've got a goal to achieve and you're using our physics and chemistry understanding to relate that goal to the possible design. Now we're going to continue building on this. In the work we just did, we said, okay, that's a chemical reaction. But what if it turned out that that was actually settling? So what does that change, if anything, about our understanding of the system so far? And as a quick reminder to you, settling can be expressed as a first order rate coefficient, where the K that would describe settling is equal to its settling velocity, Vs, divided by the depth of the pond, H. So what we're essentially saying is we could replace that reactivity term, KVC, with a new term that looks like settling velocity times area times C. So what you should do right here is hit pause and reflect on whether or not you think this is going to change anything about your calculations, and when we come back, we'll work through it. Welcome back, everybody. Great job on that pause. So we're going to keep cranking through this problem now. We'll talk about the solution to this in class, or perhaps it will become apparent as we work through the remaining parts of this question. So I'm going to punt on part D for a minute, and I'm going to go back to E. What is the settling velocity of the pollutant? And so to solve this, we need that fundamental understanding that the settling can be described as a first order rate coefficient or as a settling velocity. And so I'm going to use this equation to go ahead and plug in the values I know. 0.01 per hour for the removal rate as a first order rate coefficient, and convert that into units of per day. Settling velocity we don't know, depth we do, and I get a settling velocity of about 0.72 meters per day. Right, so if this is left sitting in a water column for a day, it's going to settle about 72 centimeters. Now, looping back to part D, right, does this have any bearing on our removal rates? Or if we wanted to modify our removal, would we want to make the pond larger in area, or would we want to make it deeper? And so to draw this out, let's think of our pond or our lagoon as the box on the left-hand side of the screen. And in the red pen, what I've done is increase its area, basically doubled it. Right? In orange, we could also double the volume of the pond by digging it deeper. Right? So instead of 3 meters deep, it could be 6 meters deep. Does that have any bearing on removal? Well, let's take a look at what happens in that term. We know that removal by settling is sort of fundamentally this settling velocity times area times concentration. So when we double the area, as we've done with the red pen, we're doubling the removal. On the bottom, however, when we double the depth, what we find is there's not a change in removal. So when a client says, hey, I want to make my pond twice as effective, I'm going to double its volume by digging it deeper, our answer should be, no, that's going to be a waste of your money. You need to make its area larger if you want settling to remove more of that pollutant. And we're going to go ahead and explore that on some of the coming slides here in a little more detail. So if settling is the mechanism, increased removal requires a larger area, not a larger depth. Now, as sort of an advanced move for you, if you're feeling like you're on top of all this, you should pause here and ask yourself, what if this was a chemical reaction? So in the case of settling, I've showed you that area matters and depth doesn't. Would that be true if it was a chemical reaction, not a settling process? Why or why not? So that's something you ought to be able to prove to yourself if you're really on top of all of this material. All right, now let's say that the pond is limited to 3 meters deep. We've got shallow bedrock perhaps, like we have here in Bloomington where I'm sitting right now, or perhaps there's some sort of equipment that won't work if you dig the pond deeper. So let's try and derive some relationship showing removal as a function of lagoon area. And so we already had a relationship about removal previously, but it doesn't have area in it explicitly. And so the trick here is to remember that the volume of the pond could be approximated as its surface area A multiplied by its depth H. And so you can go ahead and make that substitution. Now, for an advanced move, and just to prove to yourself once again why this H doesn't matter, right? When I look at the equations written in blue here, I see depth down in the denominator. And so it gives me a little heartburn right now. Didn't we just say depth doesn't matter? Now depth is showing up in my equation. What gives? And so the trick here is we can recast that that removal from its first order rate coefficient form to its settling velocity form. And you see you've got two h's down there that'll cancel one another out, and we find that removal is equal to discharge divided by discharge plus settling velocity times area. In other words, depth isn't there anymore. That's in good agreement with what we talked about on the previous slide, and all is well in the world. And what that equation looks like if we plot it out is here. And once again, just highlighted in red is the case that we solved initially, where for a 500 square meter lagoon, we ended up with just about a 20% persisting through the pond, or an 80% removal rate. Okay. Now, if we've got a limitation, if we are stuck at 500 square meters, is there any way to increase removal? Right? And we've already proven to ourselves, no. Increasing removal by settling requires an increase in area. And so what should we expect this relationship to look like? If H isn't there, it's not on the right-hand side, that means nothing should change. So it doesn't matter if the depth of the pond is 1 centimeter or a mile, you're not going to change removal rates. And indeed, if you go through and take the trouble to plot that in Excel, you get something like this, where the removal that you find has absolutely no change, even if you make the pond anywhere from, I think I plotted half a meter up to 11 meters here just to drive the point home. Well, fixed area gives us a fixed removal for settling. And again, these are specific to settling, and you should be able to think through on your own if that would matter or not in the case of a chemical reaction. And we'll talk about that in our next lecture. All right, now finally we can make this a little bit more practical. If we know what we want in terms of an area, that still might not be enough to complete our design. So for example, if a liner might be required for our pond, then its actual geometry is going to matter too. So let's think about an idealized lagoon that has some dimensions of length L, width W, and depth H. And of course the top of it has a surface area of A. And so if this is like a box that's open on top, the amount of liner we need, we could sort of think about it like we were taking that box and folding down the sides of it, where pink would represent these two vertical walls on the long edge, the box is shaded in yellow would represent the sides, and of course that bottom would have an area A. And so the area of liner you would have to purchase needs to account for the bottom, the two short sides, and the two longer sides. Right? And so even given an area of pond, you still have decisions that you get to make as the designer about what shape it will be. Now here I'm pitching it as a rectangle. If you're feeling creative, you could make a circular pond or an ellipse or something more complicated. So we're just working through kind of an easy example here. So given that you know, for example, an area that you want to have, a depth that you're able to have, we still don't know what design is most economical, meaning uses the least of that liner material. And so you can go through and you could use a design like this to relate the width of lagoon to the length of lagoon to the surface area, and do sort of a minimization problem where you might actually go in and find what is the most efficient shape of pond terms of the materials used to create it. Okay, so the goal of this example was really to help push us to thinking about CSTRs, continue working through our mass balance problems, and see how we can take that mass balance equation that we've been using to analyze CSTRs and operationalize it, or use it to design something that we might be interested in. Thanks for sticking with me, and I will see you all back in class.